Okay, welcome to the 58th lecture. So, we have been discussing about the control moment gyros. So, we have looked into the its a working principle and that was a pretty simplified one. Okay. So, now we will do some mathematics and see the difference between the already I have through the figure I have shown you difference between the control moment gyros and the basic gyrostate. So, this is basic gyrostate and this is the control moment gyros. So, how do they differ, and this part is very important which we have to keep in mind. So, if you remember for the gyrostate, the angular momentum h we have written as j double bar dot omega and plus h, where this is the angular momentum, this is moment of inertia, this part is moment of inertia dyadic. So, this is inertia dyadic of the whole satellite including the rotor wheel or simply the rotor wheel. Reaction wheel and this rotor, which are the momentum storage devices or momentum transfer devices, we use it in separate sense. We will discuss that issue, we will leave it for the time being. So, inertia dyadic for the whole satellite, this relationship we have derived, and this is the angular momentum, and therefore, this is the angular momentum of the whole satellite. Okay. But inside there is a device which is rotating. So, this is the angular momentum of the rotor with respect to the satellite. So, that gives you the total angular momentum. So, this is a satellite and there is a rotor here, okay. And suppose that this rotor is not rotating. So, what will be the moment of inertia of this, which is we are writing as j double dot, okay. And then if this body is rotating at omega angular velocity. So, this is your associated angular momentum. In this case, we are assuming that this wheel is not rotating. If the wheel is rotating with respect to this satellite, so you need to add further one part. So, this is a one part and another part, this is for the wheel with respect to the satellite. So, the same equation is written here, and therefore, if I take the derivative of this dH by dt. So, with respect to the E frame, this is your inertial frame, okay. So, we can write it as d by dt and breaking it, this is with respect to the body axis. Okay. In the body axis, this moment of inertia of the whole satellite will not change, and then omega cross, this is one part, and for this part then you have similarly h dot and plus omega cross h. So, that means what we are doing, that this is rotating with respect to the satellite. So, this is suppose its angular momentum vector. So, as the satellite rotates at this omega, okay. So, therefore, because of this omega cross h, the change will take place, and the another change we have to write if the wheel itself is speeding on this axis. So, for that you have to write this part. Okay. So, this is for the wheel speeding with respect to the body axis, okay. Because here it is a fixed in the body axis, its a direction is fixed. Okay, and thereafter what we did, that we rearranged the terms and rewrote the whole thing. So, go to the next page. So, we have dH by dt, this equal to omega dot plus omega cross h dot, this is with respect to the body frame, and plus omega cross h. So, this h dot, this implies h 1 dot E 1 cap plus h 2 dot E 2 cap plus h 3 dot E 3 cap. This is what it means, and we have written it in the other format also. So, if we try to write this side as the torque acting on the system m, okay, so this is m, suppose we write this as the m external. Okay. So, m external, this term, then you will have j times omega dot plus omega cross, and this whole term from here to here, this term we can write as say u. So, or u or minus u, whatever we can write, both will be equally valid. So, let us make it minus u here in this place. So, if we write here minus u, so minus u will be present here in this place, and we can bring it on the left hand side. So, in this context, how it is appearing, that this is your whole satellite j double dot, this includes j double bar, which is the inertia dyadic, it includes also the wheel inertia. Okay. So, this is as if this whole satellite is rotating. For this you have written the equation, but what is the modification? If this quantity is 0, it is free from the external torque. So, your the internal system you are using, and you are writing as minus u, and you have taken here on the left hand side. So, this minus u from that place is h dot with respect to the body axis, which I will drop that notation and simply write this as omega cross h. Okay. So, this defines the dynamics of the rotor wheel, and here this can be your control input from motor, control input from motor. Okay. So, this is your basically in control notation, this is simply control torque or the control input, and as a result you are getting the other side, it is a change in. Okay. And so, if you apply a torque on some system, okay, if you are applying this torque, let us say this is this quantity we are writing as minus u, Okay, so, obviously, the main body will also feel a torque in just in the opposite direction. Okay. So, applying a torque or either you are writing this as the u here. Okay, so, just opposite of that anyhow if you change the sign, if this is if you are writing this as minus u, I will show this as u. If you write this as plus minus u, so here the plus sign will come. So, by controlling your rotor, you will be able to, this is the control input or the torque applied to the rotor. So, if you apply this torque, the rotor will change like this, and the same torque will also be transferred to the in the opposite direction to the main body, okay, which also includes your the rotor, okay, which is here in this place. This also includes the rotor. So, this way you will be able to control the attitude of the satellite. So, this is using, there is just one wheel here shown, and for the multiple wheels what we have done, that here in this equation we have just inserted a summation sign. Here we inserted a summation sign, we wrote it as h I and this as h I, if you remember. So, this will be the summation with u I, okay. Here this will be the summation with u I, and then you can break it along the 3 axes, then you can get the corresponding solution. Okay. So, you see the how the changes are applied. So, this part I am deleting from this place, not to confuse you. If you have multiple rotors along the different axes, so just put a summation there and use that to solve your problem. Okay. So, this is about the gyrostate. Now, we are going into and looking for the control moment gyros. So, how they are differing. Okay. So, in the case of the gyrostate, your this direction was fixed with respect to the body axis. Okay. This direction we have kept it fixed, because it is fixed inside the body axis. So, with respect to this axis, this remains fixed, this one will remain fixed. However, in the case of the control moment gyro satellite, so you have the satellite here, okay, and as you have seen that your rotor is changing its direction. So, because of your the arrangement you are using, the outer frame in the especially in the double gimbal control moment gyros, this is the outer frame, and then we have the disc here in this place, the outer frame, inner frame, and this disc. So, because this can rotate by psi here, okay, and this can rotate about this by theta. So, psi and theta, and this rotation about its own axis we have shown it by phi. So, the angular momentum of this rotor disc, which you are writing as h w, this wheel, it can be oriented on the surface of a sphere anywhere. How we are doing on the sphere? For suppose this is my reference axis here, x axis. So, from here I measure any angle, this is the y axis, and vertically this is the z axis. So, starting from this place I show it by psi, this angle. Okay. This we have looked while discussing into the orientation problem right in the beginning of this course. Okay. So, if h vector, suppose it is h wheel is directed along this line. So, this will come to this position once you have rotated from this position to this, and thereafter I can rotate it from this position and bring it on the surface of the sphere anywhere. It can go, and this angle, let us say this angle is theta here in this case. So, h vector comes here in this place. So, by rotating by psi and theta, I can point this h vector on the surface of a sphere in any place. Okay. You can go to any place. So, the each vector, if I show this as the my body frame E 1, E 2 and E 3. Okay. So, your each vector here which is the pointed by the rotor and the frame we are assuming to be the massless, this frame and this frame it is a massless, these are not massless, they are having masses. Okay. So, for that the detailed calculations are done, analytical, and thereafter the it is computed. Okay. So, so that way if your gyroscope, suppose it is located here in this place itself, or it may be located somewhere else. So, this each vector which is we have shown in the previous case as this one, this h vector which is related to the wheel rotation. Okay. I will write as h w here. So, this can rotate with respect to this body anywhere. Okay. This body itself is rotating at the rate omega, but this wheel also it can rotate, it can get oriented here in this direction, it can go here in this direction. Okay. It can keep changing its direction because of this psi and theta. Okay. So, there is a difference between the gyrostate and this control moment gyro satellites. Okay. And because of this the problem gets complicated. Okay. And if you take the frame masses, this outer frame mass and the inner frame mass, then the situation is much more complicated. So, let us again write, this is the total angular momentum for the whole satellite. So, from the previous our discussion, if the frame is massless, so we can write this in the terms of h wheel. Okay. H wheel or h, they are same, h wheel is identically h. Okay. Because there is the, you are assuming frames to be massless, frames are massless, and therefore, only this one will count. So, either if I write here h w or h is the same. Okay. Now, if I do the differentiation with respect to the E frame, okay, that is with respect to the inertial frame, d by dt with respect to E frame. So, we will have here on the right hand side d by dt and following our earlier discussion, for the main body we have j times w dot. Now, remember that if this is the satellite, okay, and this is the rotor, right now it is oriented like this. Now, after some time the same rotor it gets oriented here in this direction. Okay. So, until unless this is an sphere, this rotor is an sphere, this j will also not remain constant. So, if I am writing like this, so I am assuming here the rotor is a sphere, rotor is a shell or a sphere, a shell or a sphere, and only then this is applicable. Otherwise, the moment of inertia of this will keep changing, the satellite will keep changing as the rotor tilts here and there in other direction. Okay. So, for simplicity it is assumed that this does not change, okay, and it can be the case where it is a shell or either a sphere. So, instead of a wheel, means instead of a disc, you are using a sphere which looks like this. So, this is a sphere, okay, and it is rotating on this axis. So, whatever the way it tilts, so it is a moment of inertia, it does not change, okay, along any axis, because whichever the three orthogonal direction you choose for a sphere or a shell, they remain the principal axis direction. And therefore, it does not make to the difference to the moment of inertia of the whole body. So, for this case this is applicable what we are discussing here. So, this when we can write as omega cross j double dot omega plus this part. So, ds by dt. So, this is the angular momentum of the this body, this wheel with respect to the this is the wheel. So, this is angular momentum of this wheel with respect to the body. Okay. So, if we write it in this way, omega cross this is the h dot plus. So, this h dot is with respect to the body. Okay. This is the main body here, and then omega cross h wheel. So, the term h w it is appearing h is appearing here in this place also, but there is a difference between this h dot and the h dot which is present here. Okay. In the previous case your h dot can be only by speeding of the wheel. Okay. While here in this case this is also tilting. Okay. This omega. So, what you are doing exactly that there is a vector inside, this is a suppose h vector. So, as your the body frame rotates with angular velocity omega. So, this h also changes. So, for that you have written this omega cross h w. But beside that so, this h w it changes because of the rotation of the whole satellite, but in addition to this your this axis itself is tilting. Suppose if I fix another axis here in this place, I fix here another axis. Okay, so, if I fix another axis here in this place, so this axis is rotating with respect to this body axis. This is your body axis E 1, E 2 and E 3, and this body axis itself is rotating at the angular velocity omega. Okay. And inside this body axis you have the rotor here, to which I am attaching another frame, and this frame is also rotating with respect to this body axis, means the double rotation is involved. The body itself is rotating, and with respect to the body also the wheel is or the your cell this is rotating. So, this case this term here and this term here, they are different, they are not the same, and this difference you should note, and this is a very important part. Okay. So, if we use this and then we write it here in this way, the torque, the m is the torque, the external torque acting on the system, and of course, here we are assuming that this is not changing much, and therefore, this is remaining almost constant. So, we write it like this, and then omega cross j double dot omega, and this quantity we write as here as minus u. So, you can see that m external plus u omega cross. This is a very simplified model. So, that means you have the other term minus u, this equal to h dot wheel with respect to the body axis and plus omega cross h w. So, this is the torque that you apply on the wheel. So, as a result the angular momentum of the wheel, it will change its direction. Okay. In addition, we can have the wheel also speeding up on this on its own axis. So, if that happens, that we call as the variable speed control moment gyros, and if it is a double gimbal. So, variable speed double gimbal control moment gyros, variable speed this is double gimbal control moment gyros. So, we do not have a space here. So, we will come to that topic again. So, what I was stating that in addition, if your wheel is also speeding on its own axis, so that means you have 3 degree of freedom. One is coming from psi, another is coming from theta, and another will be for phi. Already it is rotating at the rate phi dot, okay. But phi dot you can speed up. So, that constitutes another degree of freedom, and this can be used to produce the 3 axis control torque. While here in this case with psi and theta, only if they are varying, you can produce only 2 axis control torque. Okay. So, these are the subtleties involved with the control moment gyros. So, this issue we are going to discuss afterwards. Okay. For the time being, this is the situation. So, using this u here, then the control can be planned for the control moment gyros. Now, the same problem what we have done here, okay, we look through some other perspective. This is omega dot. It is a very important to discuss this part. Without this, it will be incomplete. Anyway, let us start. Say this is my main body, and here this is my control moment gyros, whose axis can tilt. So, this is your CMG, and this is the main body. So, the angular momentum h, this is h total angular momentum. I can write in the h angular momentum of the main body and plus h angular momentum of the wheel. How does, what is the difference here? I will put a notation here. Actually, this is the absolute angular momentum. So, I need to make it sure that it differs from the previous one, because here I am not writing the whole body. Okay. This is not for the whole body, it is only for this not includes, this does not include the CMG. Okay. So, this is CMG separately. So, the absolute angular momentum of the CMG. So, you can see the difference. In the case of the gyrostate, what we did, that we took the angular momentum of the whole system as the angular momentum of the whole satellite, including the gyrostate or the rotor. So, there the rotor mass was also included, here rotor mass is not included. So, rotor inertia is not included, rotor inertia not included. So, this is being considered separately here in this place. That means, we are taking this satellite, the body, and there is a hollow inside in which you have the CMG located here. So, this is free body diagram FBD of the body, and here there is your FBD of this CMG. Okay, and these two angular momentum we are counting separately. So, this is absolute angular momentum, while in the previous case for the gyrostat what we have done, we have taken the angular momentum of the whole satellite including the CMG, and plus with respect to the this satellite, this is rotating on the axis. So, that we included separately, okay, and that we have written as H w. So, that part we wrote as j double bar omega and plus h. Okay. So, this is with respect to the body axis, with respect to this axis in the case of the gyrostat. So, this is basic difference we have already discussed. Now, here in this case you see that I have separated this part and this part here. So, your H total, this total I will drop here. So, this can be written as I double bar dot omega. This does not include the this will, okay, and plus the this is the will, inertia of the will dot omega will. So, this is the absolute angular velocity of the will. This is the absolute angular velocity of the will. So, H dot means d by dt with respect to the E frame, we have to work with here omega w, this equal to omega plus omega s. So, once we differentiate this part as usual for this part, and we are assuming that as a rotation of the wheel the I does not change. Okay. So, once the CMG is working, so okay, in this part there is no question of that, because it is a separately we are considering. So, there is no need of that assumption. So, just remove this part. Okay. So, I times w dot, okay, this is with respect to the body part, we can break this into d by dt with respect to the body axis. So, this I double bar comes out, this inertia dyadic, and we get here I times w dot. So, this is the dot product here, and then omega cross and plus for this part. So, d by dt with respect to E Now, this part we can write here as d by dt with respect to the body axis. Here in this case, this body axis will, because we are considering the this frame itself, okay, we are considering this wheel as a separate body. Okay, so, while writing this part, this is with respect to the inertial frame. E is the inertial frame. So, this I have to consider it that we are taking this wheel as a separate entity. So, I fix a frame here which is a body frame here, okay, to this rotor which is rotating. So, while writing this equation, then I have to write with respect to, say, this is the wheel axis. So, I have to write it like this. This is with respect to the wheel axis, and then I and plus omega wheel cross I double bar, this is wheel, okay. So, see the difference here, okay. This W W, this is by W W, here this is by omega, because I am assuming that this body axis is fixed to the body axis for this one, which is this W I have indicated by W, I can write as E 1 prime, E 2 prime, E 3 prime. For the main body I have taken axis as E 1, E 2 and E 3, and outside this I have taken capital E 1, capital E 2 and capital E 3. This is your inertial frame, this is inertial, this is the satellite body frame, and this is wheel body frame. Okay. So, and because of this your omega W is appearing here, this is very important to note, okay. Not omega, this omega will not appear here. If you do this, then this will be a blunder. So, we will continue in the next lecture what we have discussed, and we will derive this with a shorter method. Okay, thank you very much for listening.